have Tzachi Lior, that you probably all know from here. He's our seismologist. And yeah, go on.
Okay, so thank you.
The shortest introduction.
That's the way to do it. Okay, so in this talk I'm going to show you most of what I've been doing since I got here, roughly 3.5 years ago. I'm going to talk about how we can harness fiber optic sensing for seismology, specifically to study earthquakes. So the data that we're using looks like this. We're used to looking at seismograms as a single time series, but now we're looking at it as images, matrices, where we have distance along the fiber as a function of time. This is an earthquake that occurred roughly 2 years ago in the Kinneret, recorded along road number 6. We have a fiber there. And we can see distinct phases, P wave, S wave, and a rich image of the seismic wave field. I'm going to go deeper into this data and what we can do with it to seismology in this talk. So 3 parts. I'm going to say a few words about how this technology works. It's called distributed acoustic sensing, or DAS. And then I'm going to show you 2 use cases. First of all, the use of DAS for earthquake early warning, and for to get more accurate earthquake source parameters, stress drop and seismic moment. So the basic physical principle that allows for measurements to be obtained using optical fibers is demonstrated in this image. So we have a laser source and a plastic rod that mimics an optical fiber. We see that light is introduced into the fiber at this end. Most of the light exits here, but we do see that some of the light exits on this side. And we can actually track this light beam as it goes through the fiber. Now, the reason that some of the light exits here, and the actual reason we can see this beam of light, is because the photons emitted into the fiber interact with various heterogeneities inside the fiber. The fiber is silica, but it has various anomalies, density, and material. And when the photons enter the fiber, some of them interact with these anomalies, and they are backscattered towards the light source. The reason that we see this light beam is because these photons are scattered back into the camera. Now, when some acoustic wave field, and it can be an earthquake, it can be someone walking by the fiber, some, sonic boom, anything that causes the fiber to slightly stretch and compress, the location of these anomalies changes. And because the location of these anomalies changes, the phases of the backscattered light also changes. So the idea is we have this interrogator unit that has a computer, a light source, and data storage, and it emits laser pulses into the fiber. When an earthquake occurs, the fiber slightly stretches and compresses. These heterogeneities change location, and the light returned to the interrogator changes its phase. The interrogator unit knows how to convert these phase changes into actual measurements of strain or strain rate along the fiber. Now, if these last 2 minutes were Chinese to you, the important thing to understand is that this is the data that we get. We get this matrix, distance along the fiber as a function of time, and we have a time series every roughly 10 meters. So this is an earthquake that occurred offshore Greece in a sedimentary basin. We can see clear arrivals of P waves, S waves. Because it's in a basin, we see reflections from the edges of the basin towards the center for P waves, and again for S waves. We have a very rich image of the seismic wave field inside this basin. And we can use these very detailed images of the seismic wave field to both study earthquakes in much greater detail and to study the subsurface beneath the fiber. So DAS allows us to turn basically any optical fiber into a large array of seismic sensors. We said every 10 meters we have a seismogram, and we can get these measurements over very long distances, more than 100 kilometers. This is an example of one fiber that we have along road number 6 that continuously records seismic waves. We can also use fibers located offshore, and this is one fiber I used offshore France, south of France.
Itzhak?
Yeah.
These are dedicated fiber optics for your research, or you can use...
I can use whatever. One of the limitations is that the fiber has to be a dark fiber. It has to be something that is not used for telecommunications at the time. So this specific fiber, I can't really name the company that operates it, but this company has linear infrastructure that they want to monitor for leakages and theft, and they use the same technology to monitor the fiber. Along the way, they record seismic waves and earthquakes, and we can actually use this technology both to monitor infrastructure and to study earthquakes. But
you can distinguish if the earthquake will occur in this side or other.
I'm going to show you in a few slides. So one of the problems with current measurements of seismic waves is that most of our stations are on land. We don't have many stations offshore, but what we see here is the distribution of optical telecommunication cables offshore. So if we can use even a fraction of this vast underwater network for seismology, we would essentially fill in this large observational gap. And I'm going to show you examples from earthquakes recorded on offshore fibers as well. The main advantage of using DAS is that instead of just having one time series where we see the arrival of the P wave and the S wave, now we are actually adding the spatial dimension. We have thousands of seismograms along tens of kilometers long fibers, and we can also see the velocity of these waves. We can see fast waves when we get the body waves. We can see slower waves when we have scattered waves or surface waves. And another cool example is what we see here. This is a seismogram recorded at one virtual sensor along an offshore fiber in France. And if I would see this time series on a seismogram, I would probably think that it's some generator or a truck passing by or someone walking. But when I see this time series over many different channels, I can see that these are actually plane waves. And I can actually understand what this signal is. If I would have seen it only on this one station, there is no way I could understand what this signal is. And then I can also apply very intricate signal processing techniques like FK transform, 2D Fourier transform, and see that this energy is concentrated here. I can see that the velocity is 1.7 kilometer per second. And if we have time in the end, I can tell you what this signal is actually. So how can DAS help us study earthquakes? We can obtain measurements in hard to reach places like underwater or boreholes. We know that most of the largest earthquakes on Earth occur offshore at subduction zones, so this actually brings us closer to the hypocenters of these earthquakes. We have continuous measurements in both time and space that allow for more robust earthquake detection and location. And when we study earthquake sources, we can average these observations over many virtual sensors along the fiber. So the first use case is the use of this technology for earthquake early warning. And this is something that these early warning systems are already operational, not fiber-based, but seismometer-based. They're operational here in Israel, in California, in Japan, many places around the world. And the idea is that if we know where earthquakes occur, we know that they occur along active faults, we can place our sensors close to these faults, and then we can analyze the waves emitted from an earthquake as early as possible, everything done automatically, quantify the size of the earthquake, and if needed, issue alerts to more distant regions like cities. This is already operational in Israel and already saving lives in many regions around the world. And what I'm showing you here is how we can use this fiber-based technology to improve early warning. So I'm showing results from this paper. It was actually published a few days before the 2023 Turkey earthquake, so it caused a lot of media attention because it can really improve the alert time for earthquakes by roughly 30 seconds in some cases. So these are the four basic procedures we need to apply to provide early warning. First of all, we need to detect an earthquake and be sure that it's an earthquake and not some anthropogenic noise like someone jumping near a station. We need to locate the earthquake. Then we need to estimate the size of the earthquake, magnitude and stress drop, source parameters. And once we know the location of the earthquake and its size, we can predict ground motions to distant location and decide where and if an alert should be delivered. There are a few limitations to the classic approach of using seismometers for early warning. First of all, we require at least 4 detections, 4 different stations to detect an earthquake in a limited time to be sure that it's actually an earthquake and not some anthropogenic noise. And this is a problem for urban environments with a lot of anthropogenic noise and for sparse networks where we don't have many sensors and it takes a lot of time for the seismic waves to reach the 4th closest station. Yeah.
Where does the number 4 come from?
Trial and error. There are different approaches that use 2, but the standard approach, what they use in California and in Japan, they use 4 stations just to be sure that it's an earthquake and not something else. I mean, the chance that you have 4 people jumping near 4 stations at the same time is not that high.
Also location.
Yeah. There's another problem with the edge of the network, especially in marine environments, like here in Japan. The trench is somewhere here. The 2011 Tohoku Oki earthquake occurred here. It took waves emitted from this earthquake 120 seconds to reach the Japanese mainland. So only 120 seconds after the earthquake started, we knew that it happened. And this significantly delays early warning. These 120 seconds could really help the people of Japan get ready for this earthquake. To do so, we need offshore observations closer to the subduction zone. It's also a problem here in Israel because we have observations only at one end, at one side, of the Dead Sea Fault. We don't have access to stations in Jordan. And telemetry delays, because we have stations sparsely distributed along the land, they need to communicate between themselves, keeping in mind that we need at least 4 stations, and these telemetry delays also take time from the early warning. So I'm going to show you some results from earthquake detection and location, the work Shachar is doing, and focus on these 2, magnitude estimation and ground motion prediction. So what I'm showing here, are results for this earthquake that occurred here along the Dead Sea Transform, recorded by this fiber along road number 6, 66 kilometers long. And let's see if I can pause the movie. So what we are going to see in this movie is the earthquake as it is being recorded, so with time from the beginning of the earthquake. And what we'll see here is the location effort of this earthquake. Now we see the P waves. When P waves are recorded, we can almost immediately determine the direction from which waves arrived and draw these cones towards the actual location of the earthquake. And when the earthquake is recorded by more segments, we have more of these cones directed at the location of the earthquake. Already with a P wave, we can have a very reliable location. Now the S wave is going to be recorded. We have additional beams, cones pointing towards the earthquake. And we also have these rings corresponding to the time between the P wave and S wave. This time corresponds with the distance between the fiber and the earthquake. So I'm not going to focus on Shachar's work, but the paper is out. I'm going to show results for magnitude and ground motion prediction. We have 2 main obstacles in harnessing DAS for early warning. DAS measures strains, while magnitude requires ground motions. All the models that we have to estimate the magnitude rely on ground motions, on displacements, velocities, or accelerations, but what we actually measure is strain, how much the fiber stretches and compresses. So we need to convert strains to ground motions in real time, which is a challenge. The second problem is that we don't have enough seismic data. This technology is relatively young. We don't have many large earthquakes recording using DAS. So taking a data-driven approach, either empirically or AI-driven, is virtually impossible because we don't have recordings of large earthquakes for which early warning should be issued. So let's start with the first obstacle. The way that we usually convert strains to ground motions is using this simple relation. We can write strain as the spatial derivative of displacement, du to dx, and then using the chain rule, we can break down du to dx to du to dt, which is actually the velocity, times dt to dx, which is 1 over the apparent phase velocity. So we have 2 velocities here. This is a velocity for the movement of the ground, orders of centimeters per second. And this is the velocity of the seismic wave, which is 100 meters per second to kilometers per second. So to convert, this is for strain, this is for strain rate corresponding to ground accelerations. And to perform the conversion, we need to take strain rate multiplied by the apparent velocity. Sounds simple, but it's not that simple because the apparent phase velocities are a function of time and space. This is a simulation of an earthquake. We see different waves, P waves, S waves, and different surface waves and scattered waves. And we see different slopes, meaning different velocities for the different seismic waves. So to convert properly strain rates to ground motions, we need to know the apparent velocity for each of these phases. Another problem is that apparent velocities change also as a function of distance along the fiber. This is a result of the subsurface material beneath the fiber. An earthquake recorded offshore Greece. This section of fiber is over a sedimentary basin, so we see very low velocities. And this segment of fiber is over exposed limestone, much higher velocities. There's also relation with the signal-to-noise ratio that I'm not going into, but we do see different velocities. These lines are almost vertical, although it's difficult to see. And these lines have a much gentler slope. So we need to consider the fact that apparent velocities are functions of of space and time. The way that we do the conversion is using a slant stack transform, which is similar to our Radon transform. The idea is to take a limited fiber segment that has several traces, several channels, and test different slopes corresponding to different velocities, and check which slope best describes this plane wave. So we're checking different slopes, px0, px1, px2, and we see that for this plane wave, px1 best matches what we see here. For this wave, px0 provides the best fit. This is time, this is slope or velocity, and this way we can get a time series of the velocity as it changes. We can perform this procedure to various limited fiber segments along the fiber, and also see how the apparent velocity changes as a function of space. This is an example. So an earthquake recorded offshore France. At the beginning of the S wave, we see almost vertical lines, very fast waves, and immediately after, slower waves, much gentler slopes. When we use this approach to get the apparent phase velocity, we see fast waves at around 2 seconds when we get the direct S waves, and immediately after, 3 seconds and onwards, we see much slower waves. I'm not going into the details of the conversion. We do see that this image is slightly different than this one in terms of color code. But the conversion is much more reliable when we take into consideration the different velocities of the different phases. So this is the first obstacle. We have a way of converting strains to ground motions in real time. The second problem, that we don't have enough seismic data. And I'm going to show you what they're doing in California. So in California, they have a problem with subductions and earthquakes that occur offshore. Not only in California, all along the western coast of the United States and Canada. And they're trying to implement distributed acoustic sensing based early warning. And they're using this empirical approach. The idea is to measure the strains in 2 seconds following the arrival of the phase, the distance, and they have 2 empirical constants, and then they get the magnitude. This equation was calibrated using this data set. So we have magnitude and distance, and you see that most of these earthquakes are relatively low magnitudes, below 5, and distances of 10 kilometers onwards. The data that's actually interesting for early warning is here. So constructing this equation using this data set may not necessarily extrapolate well to earthquakes that occur here. And this is the relation that they're using in California. We don't really expect it to work well for larger earthquakes for which early warning is actually relevant. So what we did here is take a physics-based approach to this problem. I'm not going too deep into what we're seeing here because this slide is going to return at the second part of the talk. But the idea is that there's a simple model that looks like this that describes the far field radiation of body waves. This is it for displacement. This is it for accelerations, just multiplied by omega squared. We're also applying high frequency attenuation to model path and site effects. So basically this is the model that we use. Calculating the RMS of this model, we have to integrate between 0 and some maximum frequency. This maximum frequency is associated with the fact that dust has high frequency noise that we want to filter out. We solve this integral, get something very ugly. We get an approximation to this equation, and we have acceleration RMS as a function of seismic moment and all sorts of parameters. Because this is analytical, the solution for the seismic moment is also analytical. The equation is not so nice, so I'm not showing it here. But we do have an analytical solution, very simple equation, that's a function of acceleration RMS, distance, and time. So in real time, what we have to do, calculate acceleration RMS directly from the time series. Because of Parsifal's theorem, we can calculate RMS either in the time domain or the frequency domain. So this is something we measure directly from the time series. The distance we know given the location of the earthquake. And the time is also something that we know. We know how much time we have of a specific phase. We have 1, 2, 3, or 4 seconds, etc. So I know that I didn't go into the details here because they're not very important to the understanding, but the idea is we have a physics-based approach to estimate the seismic moment given a few simple parameters. So we solve these two obstacles, and now that we know the location of the earthquake, we know the magnitude, we can go ahead and predict peak ground motions. The end user of an early warning system, basically all of us, we don't care about the magnitude, we don't care about the location of the earthquake. We only care about ground shaking intensity at our location. Whether we need to take precautionary measures or we can keep what we're doing and we know that the earthquake is not going to affect us. So this is the end game. This is what really matters. The ability to predict peak ground accelerations at a specific site. And early warning systems use these types of equations to determine where and if an early warning should be issued. If we have time later, we can talk about what happened up north during the tunnel explosion and why it triggered early warning. So the algorithm, just to sum up, for each dust channel in a short well-coupled segment, we convert strain rates to ground accelerations using the slant stack approach and the apparent velocity. Then we calculate the RMS for each channel. We average the RMS in short fiber segments, and then we have the RMS, we have the location of the earthquake, we have the time, we can estimate the seismic moment and predict peak ground accelerations to further location. We applied this approach to 53 earthquakes, magnitudes 2 to 5.7, at distances of up to 365 kilometers. These are only ocean bottom earthquakes. So 2 fibers offshore Greece, 1 fiber which was more than 200 kilometers long offshore Chile, and another fiber offshore France. And just to show you that what I showed you before about the empirical equation and the data used to obtain it, we have the same problem. So taking our data set and using a data-driven approach would not work in this case as well. So for the results, what I'm showing here on the right, real-time magnitude as a function of catalog magnitude, and this is 2 seconds after the arrival of the first P wave along the fiber. With time, and I'm going to go to the next slide so you can see the time increase here, we expect the data points to go up. And indeed, when I go to 4 seconds, they go up. 6 seconds, we have a good estimation for the smaller earthquakes. Here the magnitude doesn't converge yet. When I go to 10, we already see a reliable estimate for the largest earthquake. And for 15, we have a good convergence along this line. But as I said before, we don't care really about the magnitude, we care about ground motion prediction. So this is the discrepancy between predicted PGA and observed PGA. We want all the data points to be around this 0 line. These numbers are a bit hard to see, so we're going to see that with time, this is 2 seconds, all the data points are going to go a bit up around the 0 line. So this is 2 seconds, 4 seconds, 6, 10, and 15. We already see most of the data points are well distributed along this 0 line. This can be improved with site-specific corrections, but overall the fact that it's evenly distributed around 0, give or take evenly distributed, says that this system, this algorithm works well.
But when you say about the y-axis, what does it mean? How much error do you have? What is the kind of errors you have?
So the standard deviations for Chile are 0.7, for Greece also 0.7, and for France 0.6, which is relatively good compared to other ground motion equations. And it also works well for these 3 different regions using the same approach. So these are the same results, 4 seconds, 10 seconds, and 15 seconds. We see that the magnitude and the estimation of ground motion keeps updating with time, which is very advantageous for larger earthquakes, whose rupture takes tens of seconds, maybe minutes to evolve. Another 2 interesting results from this study. This is from the Chile data set. The fiber is deployed here from the on-land location and goes relatively parallel to the coastline. These are several earthquakes recorded along the fiber, and at the time that the S waves reach the shoreline, we already have a reliable estimate of the magnitude. So here we have catalog magnitude and real-time magnitude, very small discrepancy between the two. And on the right, this is a very interesting result. How much additional gate time we would have had if we used the fiber instead of seismometers on land. So we see that for earthquakes that would occur very close to the fiber, very dark red, we have additional 25 seconds of warning if we use dust compared to seismometers. We also see that on land, where the seismic network is sparse, we don't have any stations here, we get a few seconds of additional alert time if we use fiber-based early warning compared to seismometer-based early warning. And this is significant when we talk about offshore earthquakes, like what I showed at the beginning with the Tohoku Oki in Japan, bringing us closer to the hypocenter of earthquakes and basically providing more alert time for devastating earthquakes. So to conclude this part of the talk, the magnitude estimation and ground motion prediction are theoretical, not data-driven. We see that it works well in various locations, Chile, France, and Greece. I also have results for Israel, not shown here, but it also works equally well. I didn't talk about the self-consistency, not going to the details, but another important thing is that we get continuous magnitude and ground motion updates. If we use the California approach that only uses 2 seconds, we would underestimate the magnitude of large earthquakes, which takes time to evolve. We also saw significant time gains for offshore earthquakes, and basically this approach is low cost if we have access to an optical fiber, and ideal for developing countries, even for places like Chile, where the seismic network is not so dense. So this was the first part of the talk. Now to the second part, I'm going to show you how we can use the same approach to get more accurate magnitude and stress drop estimates. Going back to this model, and now a bit more into the details. If we take a seismogram of either P waves or S waves, convert it into the frequency domain and clean it of the effects of path and site, we expect to see something similar to this model. This is for displacements in log-log scales. Low frequencies are proportional to the seismic moment and the hypocentral distance. This is actually how you measure the seismic moment of both small and large earthquakes. Then we have a corner frequency that is proportional to the size of the rupture and also to the stress drop and the seismic moment. And above the corner frequency, the spectra falls off at a rate of frequency to the power of -2. That's why the model is called omega squared. Stress drop is proportional to the seismic moment multiplied by this corner frequency cubed. Now a few words about stress drop. Apart from the seismic moment, the stress drop is the most influential parameter related to the earthquake source. It's fundamental to the understanding of earthquake physics, and basically, or most importantly, to the question of earthquake self-similarity. The question, or the idea that small earthquakes and large earthquakes adhere to the same physics. Whether a small earthquake is simply a scaled-down version of a large earthquake, and if a large earthquake is a scaled-up version of a small earthquake. If this is true, and earthquakes are self-similar, we expect stress drop to be constant for a wide range of magnitudes. And indeed, when we look at the compilation of global data set of many, many earthquakes, and we see here more than 25 orders of magnitude in seismic moment, we see that stress drop, indicated here by these lines, only spans roughly 5 or 6 orders of magnitude. So when we have 25 orders of magnitude in seismic moment and only about 5 orders of magnitude in stress drop, we can say that stress drop is fairly constant and that earthquakes are self-similar. But when we look at more detailed studies, and this is something done in California in different regions, most of the time we see that stress drop does increase with magnitude. So on the vertical here we have stress drop, on the horizontal we have seismic moment. We see that the fits usually indicate that stress drop increases with seismic moment. And we also see that stress drops span here 3 orders of magnitude. So this is still an open question, and there was actually a special issue now in Bulletin of Seismological Society of America to tackle this issue in a very active research area. Part of the problem with answering this question is the reliability and stability of these measurements. It's very problematic and very difficult to estimate stress drops reliably. Part of the problem with estimating stress drop is that corner frequency, so that corner frequency is very important to estimate stress drop. Corner frequency varies due to directivity and other complexities in the source. So if we have a simple earthquake model where the rupture starts at the middle and propagates radially towards the edges, we see that corner frequencies are fairly constant no matter from which direction we observe the earthquake. But we see increasing evidence that even for smaller earthquakes, we have directivity and other more complex effects. So what we see here is that the rupture starts at one end and propagates to this end. In this case, where we have directivity, we would expect corner frequency, indicated here by the color code, to vary depending on the direction from which we observe the earthquake. To get reliable stress drop, we need to get average corner frequencies all around the earthquake. And this is very problematic because we need a dense seismic network. Another problem is that the seismogram that we record is actually a convolution of what's happening in the source, what the waves experience when they move from the source to the site, and what goes on in the site itself. We have site response and we have instrument response. So if we look before at the omega squared model, we typically model path and side effects as attenuation of high frequency. So instead of seeing the red curve, we would see the black curve. And if we take the seismogram, perform Fourier transform, and see the black curve, it's virtually impossible to know how to correct it exactly to be on the red curve. And it's also very difficult to estimate the corner frequency. Another problem is that even if we get a reliable estimate of the corner frequency, these errors are cubed when we estimate the stress drop. So a factor of 2 error in corner frequency, and you see that this is log scale, so a factor of 2 is okay. But a factor of 2 error in corner frequency immediately translates to a factor of 8 error in stress drop. So DAS can really help us get more reliable estimates of this very critical parameter. We can average the estimates over the focal sphere. This is an example of the same earthquake that I showed location efforts for, recorded along 66 kilometers. We observed the earthquake from various angles, and we can get more reliable estimates if we use DAS. So with DAS, we have another problem. We usually have to account for the measurement type, the fact that we measure strain or strain rates and not ground motions. Another parameter that I didn't mention is coupling. The assumption with these measurements is that the fiber is well coupled to the ground, so that the fiber actually senses what the ground is experiencing. But if the fiber is not well coupled, and keep in mind that these fibers were not meant for seismology, fibers can be somewhat hanging or in a material that doesn't really represent subsurface materials. Coupling can also have an effect on our measurements. So what I did here is take an approach that circumvents most of these problematic issues. This is the empirical Green's function deconvolution approach, otherwise known as the spectral ratios approach. And the idea is that if we have two earthquakes that occur roughly at the same location, and they are recorded by the same instrument, they have similar path terms and the same site term. So we can write the spectra of these earthquakes as a source term multiplied by Green's function. And the Green function collects everything that happens from the source to the station. So path, site, instrument response, and with DAS also the measurement type and the coupling. So we can take two earthquakes, look at the spectra, and take the two earthquakes, convert to the frequency domain, and the idea is that if we divide the two spectra one by the other, we get rid of all these terms. Path, site, instrument, everything that we don't really care about. And then the model looks a bit different. This is how the model looks like. We have on the left here the ratio between the two seismic moments. Then we have the corner frequency of the larger earthquake and the corner frequency of the smaller earthquake. This model is much simpler to work with because we don't have to account for all these things. But with real life we still have problems because this is what happens when we apply this technique to seismometers. So here they took, not my work, they took two earthquakes and calculated these spectral ratios at different stations. What we see here in gray curves are the spectral ratios at different stations. Only when they take many, many stations and average these gray curves, they get the black curve, which can be fitted with the model. The model fit is the red curve here. So the question is, can we do better with DAS? Can we get more reliable estimates with DAS? And the fact that I'm asking also already tells you that yes, we can. So following the 2023 earthquakes in Turkey, I guess we all know that our region experienced a significant increase in seismicity. So in a work done with Asaf Inbal, we saw that much of the seismicity was actually not along the Dead Sea Fault. We see here regions with increased seismicity. This is one of these regions near Nablus. And here we had a sequence of earthquakes that are actually the same. We saw the same waveform recorded for different earthquakes at the same location. This is the first second of signal for 10 different earthquakes in the closest accelerometer, which was 10 kilometers from the source in Ma'ale Efraim. And we see that this 1 second is very similar among these different earthquakes. Also, when we look at the dust recordings, we see great similarity between the different earthquakes. So these are 10 collocated earthquakes, an excellent data set to test this method, magnitude 2.5 to 3.4. And the fiber in this time was only 35 kilometers long. And what I'm going to show you now is the real power of using dust for this approach. Because if we take one dust channel, take the two earthquakes, convert to the frequency domain, and take the ratio, the spectral ratios, we get this gray curve which is outside the limits of this figure. When we smooth this gray curve, we get the black curve, and this is the fit. The blue is the fit. Red diamonds are the location of the corner frequencies, and we see the error bars. So this is just with one channel. So one dust channel is very similar to using one seismometer. When we take 551 channels over 5 kilometers, basically we average many of these gray curves. We get this gray curve, which is much more dense, much more well-defined. The black is the smooth version, and the fit, we see it here in blue. When we take the entire fiber, we see a very good fit, R square of almost 1, 0.99. Very small errors on corner frequencies, very reliable estimates. So the strength of using dust here is that we are able to stack the different spectral ratios along the fiber and get more reliable estimates. We applied this approach to the data set. After some signal-to-noise ratio requirements, we're left with 9 earthquakes out of 10. Because the fits are so good, we require a magnitude difference of only 0.33. With seismometers, they usually require a magnitude difference of 1 unit. And this gave us 17 of these pairs, 17 earthquake pairs. What I'm showing here is just an example where the smaller earthquake, the magnitude 2.6, is the same. So the larger earthquake is different, a 3.4, a different 3.4, and a 3.3. The smaller one is the same, so we expect that the corner frequency of the smaller earthquake to be the same. And indeed, within error bars, we get the same corner frequency. Using this model, we get the actual corner frequencies, but we only get relative seismic moments. But because we have 17 of these empirical Green's function pairs, we can perform a least squares inversion to get relative seismic moments, assuming that the seismic moment of at least one earthquake is known. I'm not going into the details of this method, but it's a very simple least squares approach. And we can get accurate corner frequencies, relative seismic moments, and also relative stress strokes. So these are the actual results: corner frequency and seismic moment in log-log scales. The dotted line here is the line of self-similarity, and we do see that most of the earthquakes lie along this line. We see very small within-event variabilities in corner frequency for these earthquakes. And when you look at stress drop as a function of magnitude, it's not many earthquakes, only 9, so we don't have statistically meaningful number of data points to actually say it, but at least for this small data set, we can say that stress drop is invariant to earthquake size. And you can see that the range of values here is less than, or roughly half an order of magnitude, and if we go back to this figure, where they show 3 orders of magnitude, I can say that these results are very reliable and very robust. So, robust source parameters with dust using this spectral ratios method. We saw very reliable fits. You can see the R squares here are almost 1 for most of the fits, which facilitates application for similar sized earthquakes. And then we have more potential earthquake pairs and more reliable results. We don't need to convert strain rates to ground motions like we did for early warning, because the earthquake occurred at the same location. We actually get rid of everything related to the conversion between strain rate to ground motion. This makes this approach much easier to apply. Just a few words about ongoing work. So in this same location where the GSI cataloged 10 earthquakes, I have a student that's looking for additional earthquakes using waveform similarity, and he found over 100 additional earthquakes, very low magnitude. You can see that the magnitude here is roughly 1 or a bit below. And we do see a few interesting things, work still in progress, like we see that the larger earthquakes are deeper than the shallower earthquakes. We're working on getting stress values from these events. But we see that they are very well confined, depths of 5.5 kilometers to 8.5 kilometers. We were able to extract the strike and dip of these earthquakes. We know that these are normal earthquakes with a strike that's similar to what we know about faults in the area. And it's still an open question as to why we had a significant increase in seismicity of the Dead Sea Fault in a region where we didn't have earthquakes before. So this is still something we're working on. And just to conclude with another future work, what we see here in green triangles is the seismic network operated by the Geological Survey, which is already one of the densest seismic networks on Earth, with a station every 7 to 15 kilometers along the major fault lines. You can see here the Dead Sea Fault and along the Carmel Fault. These are the fibers we are currently monitoring. Over 200 kilometers of fiber, basically another line parallel to this line of seismometers. And I think that it's one of the densest observational networks on Earth, coupling thus with regular seismometers. And I'm sure that we will have many more interesting observations and work coming out from this data set. Yeah, thank you.
Questions?
You said something about how you calibrate. I'm assuming there's need for calibration to get the strain rate from the optical signal.
Yeah, so what we actually measure is phase rate. And there is a simple linear equation that considers the refraction index of the fiber and also a few optical parameters, but it's fairly constant, like the conversion between phase rate and strain rate. There is a problem with saturation because you measure phase, which is between minus pi and pi. So if you measure very strong deformations, you need to unwrap the phase. And this is something that is problematic for early warning, where you're interested in very high amplitude signals, and still something that people are working on.
But it's basically analytical, it's not.
Yeah, it's analytical. But they can also measure it. They can apply a stretcher that actually stretches the fiber by a known amount and calibrate it empirically. Yeah.
Can you, first, thank you very much. It was a very interesting talk, very exciting actually. So thanks. Can you use the telecommunication cables that you showed in the ocean or offshore Israel? Because we really are interested in the offshore earthquakes.
Yeah, me too. Until now, I've encountered a significant barrier in using these fibers. I know that they exist. I know that there's another fiber here from Tel Aviv to Haifa. There are a few fibers going from Tirat HaCarmel to Cyprus. From Tirat HaCarmel to Cyprus, they gave me a quota which was ridiculous. No way I can pay. They gave me a price offer, and it was
but you,
crazy.
The data is
No, it's not monitored. None of the fibers offshore are monitored. Most of them are owned by gas companies, and they're not really willing to cooperate. But I'm still trying.
But technically, you could use it while they're transmitting telecommunication data?
Usually, a cable has more than one optical fiber, and they're not using it for telecommunications commercially, so I guess they have a few available strands. So it's not really a problem. When I approached the telecommunication company that is transmitting data from Israel to Cyprus, it costs a lot of money because all the data from Israel to Europe and outside goes through these offshore telecommunication companies. And then it's more expensive. But with gas companies, that's not really the problem. They have the fibers, they're just not willing to cooperate.
If you place them in the offshore, natural variability like storms and the waves and all this are much smaller than earthquakes. I mean, it's easy to filter them.
You can filter them based on velocity. If I go back it's basically much noisier offshore because all waves are stronger. So here, for example, I focused on this, but what we see here are dispersion curves of waves propagating in the, these are seismic waves propagating in the interface between the water body and the solid earth. But we can also see surface waves. We can see infragravity waves. We can see many, many things. I'm actually giving a talk in the CEO seminar close to the end of the semester on these things.
What is it that you promised to say?
Yeah. So, do I have the figure? No, we don't. There was an earthquake in Algeria, a relatively small one, a magnitude 4. When waves from these earthquakes came to the Mediterranean, energy was converted from seismic waves to acoustic waves, and these acoustic waves propagated all the way across the Mediterranean and were recorded by these fiber optic cable offshore fans. So what we see here, these are called T waves. So we have a P primary, S secondary, T third, whatever. These are acoustic waves generated by earthquakes that propagate in the water column. And the velocity here is 1.7 because we see the projection of the velocity along the fiber, not 1.5 as we would expect. So this is an observation we couldn't have got without this dense setup.
What about tunnels?
What about?
Tunnels.
Tunnels?
Hezbollah dig tunnels.
Yeah, they're working on it with, I guess that, I'm not sure, but this technology is also used by the army for border control, for drones, for tunnels, for many things. They're working on it more in Tel Aviv University.
Economically, can fiber optics seismometers replace conventional spectrometers, or what are the advantages of a normal seismometer relative to fiber optics?
So with the fiber optics, you need the fiber, which is very difficult and expensive to deploy. And you cover a large area, but the interrogator is very expensive. Prices do go down with time, but one interrogator unit still costs much more than a standard seismometer.
You said 200K?
I said 200K at the time, but it went down. So if I go back to what we had at the end, when I showed the seismic network in Israel, it would be quite difficult to cover all this vast region with the seismometers. When I initially got here, I wanted to deploy my own fiber, and I went to Allenby Crossing around here, and then they told me you have to get permissions from רשות הטבע והגנים and משרד הביטחון. So I gave up. But like I said, this technology is also used for border control, so there are fibers deployed somewhere, and the problem is again access. Also, with getting permission to access this fiber, it's contracts and NDAs and limitations and stuff like that. Mekorot are much easier to work with. And they're also buying additional systems, one for around here and the other one, I'm not sure.
What about the international collaboration? For example, you are doing it here, and somebody is doing it in France at the same time on the same earthquake, right?
What do you mean on the same earthquake?
Let's say that you have an earthquake somewhere,
Yeah.
and somebody is catching it in station A, and let's say that you are in station, right?
Yeah.
You are station A, and Oded Nahon is station B.
Mm-hmm.
And he's using another fiber optic. Can you compare that? Can you integrate them to it? How do you do it?
We have the recording, we have the time, we know when the earthquake arrived at each fiber, and we can work with it. For example, one of the techniques that they use to image large earthquakes, and I saw a few initial results from the earthquake in Myanmar, they use seismometers located in various locations on Earth to image the rupture itself. So they use in the same time recordings from Alaska, the US, Europe, at the same time. So it's also possible to do it with DAS. The problem is data sharing. Data here is huge. I collect more than 200 terabytes of data per year. So sharing the data is still a problem. Standard seismic data is typically shared online. It's very convenient and organized. There is actually not a uniform format for that data yet. It's relatively new, so it's a matter of time before these things become more common, and it will be easier to compare different things. Another problem is that acquiring data is very expensive, so people are not sharing it. So I have my data, people in France have their data, and everybody's working on their own data set.
So, but that was my point exactly. So you don't have a collaboration